Hello and welcome to my tutorial on creating a basic transformer. You can kind of think of this tutorial as a prequel to my vision transformer video. And so we're going to be following a similar structure, and it's just going to be going through a little bit more details on transformers and how they work. So, as always, we're going to start by going through a slideshow explaining the basic concepts, and then we're going to actually convert it to Pytorch to actually build the model. So, of course, quick disclaimer, this video only contains a high-level overview of the transformer architecture. For a more theoretical video, see my attention is all you need paper reading. Right, and so there I go into a much higher theoretical detail, and I have more diagrams and whatnot. So, let's start with the basic architecture. The basic architecture of the transformer is the attention layer. This is kind of the key to everything that happens here. Now first, what is attention? Right, so to understand transformers, we have to understand attention. And so here's a diagram of a single-headed attention. Right, where first you take your input and you split it up into a key, query, and value. Then what you do is you take every key from every input token, and then you combine it with the query of any given input token via just like a dot product. Then you combine it with the value, and then you have your output. Right, so in essence, you're just taking information from all the tokens, combining it together, and then having a value so that you can have the output. Now, of course, in the original transformer paper, they also introduced a thing called multi-headed attention. And this is just a way, so now you have attention on different parts of the input, right? So the first, say, 10% of the embedding token will go through one attention, the next 10% goes through another attention, right? And then the next 10% goes through another attention, right? So you just have a bunch of different attentions. And so these are heads, right? These are attention heads. And so, yeah, you have multi-headed attention. So now you can do attention on different parts of the embedding token. So now we understand what attention is. Let's just expand the basic architecture. So, of course, in order to have attention, what you do now is you have to clean up the output. So you just have a feed-forward layer, which is just an MLP. And you can have multiple different layers of this, right? So you have one attention. So we'll call this a transformer block. You have one transformer block, followed by another transformer block, and so on, so on. And of course, you need a bunch of supporting stuff to go along, right? Like, you need to actually embed the text into a latent space so that it's easier for the transformer to understand. And you also need to embed the position, because each individual token doesn't actually know where it is. So you need to embed the position into the transformer. And that's your basic architecture. Now, let's build. Now, let's start building the actual transformer. First, I'm going to set up the virtual environment, right? So I'm just going to call this learn transformer, right? And so we're going to set up the virtual environment. And so now what we're going to do is we're going to activate the virtual environment. So we're going to activate it, and then we're just going to pip install stuff. So we're going to pip install Torch. We're going to install TQDM because we use that for training, and then we're also going to install a request because that's what we're going to use to actually get the data. Right, so we're going to be doing our own data set. Well, not our own. We're going to be pulling one from the internet. We're going to be using Tiny Shakespeare by Andre Carpentry, and then we're going to be training a model on that. And so, yeah. And so from here, we are obviously pulling in everything. And so first what we're going to do is we're going to do a similar thing to the Vision Transformer video. We're just going to go through the model itself, like step by step, cover everything that's going on there, and just do all of that. And so then from there, I'm going to write the actual training code. And the training code I'm going to go a little bit faster through because that matters a little bit less. And so I'm going to go a little bit faster through the training code. And then from there, we'll have our code. So first, let's open up transformer.py, which is going to contain a transformer. So obviously, we have our inputs, right? We have Torch, Torch.neural network. I'll just go import it as an N, and then we're going to import the data class so we can actually set up our config. This is a from data classes, import data class. Now from here, we're obviously going to make a data class, right? And so data class, I'm just going to call it transformer config. I'm going to use a capital T here. And so obviously it's going to contain a bunch of stuff, right? Like vocab size, which is going to be an integer. And I'm going to set the default to, I don't know, like 128. We are going to have the maximum sequence length. So you can think of this as like the context window of the transformer model or LLM. We're going to make a language model here, tiny Shakespeare, right? And I'm going to set this to, I don't know, 100, right? Just like a default small amount. I'm going to set the embed dimension, and that's going to be an integer. And I'm just going to set this to like 512, right? But we're not making a massive model here. I'm just going to set the clean, nice numbers. The depth, so this is the number of layers. I'm going to set it to 6. A number of heads, and it's an int. Obviously, you can't have like a fractional number of heads. We're just going to set it to 8, right? This is just a nice, clean, small power of 2. MLP ratio, so this is how much bigger the MLP will get, and I'll explain this later. This is going to be a float, and I'm just going to set this to 4. Right, so these are just numbers. You can change them. I recommend that what you do is you just go out and you just change the numbers, right? Like try a model with less heads and a higher MLP ratio. Try a model with a higher depth but a lower embed dimension, right? Like try all of these things, right? I'm going to set the QKV bias. So this is there a bias in the query keys and values? I'm just going to set the boolean, and I'm going to set that to true, right? Like a lot of these necessarily, not really, but like can't hurt to have them here. And it's also an easy way to like edit it later for like, you know, when you want to like update it. I'm going to set the drop rate to 0.1. And then the attention drop rate, I'm just going to set that to 0, right? Right, so just a bunch of settings here. Now, we're going to start with the token embedding, right? So if we go back here, we're going to start with the token embedding that actually, you know, does token embedding, right? So class token embedding. So this just allows the neural network to kind of just quickly put the like input tokens into latent space, so it's like easier to work with, right? And so again, we need to set up the two main functions here, right? Init and forward, and this is self and x. And so for init, what do we actually need here? We obviously need, you know, to actually run the imported thing, and then now we're actually going to set the embedding model. I'm not going to go fancy here. I'm just going to use the Pytorch embedding model, right? Like we're not, this is just a way to get it into a place where the transformer blocks can work, right? And so number of embeddings, well, I'm just going to set this to config.vocab size. And then the embedding dimension, I'm just going to set that to config.embed dimension. Next, what I'm also going to do, so I'm just going to set up the max sequence length here, and I'm just going to set that to config.max sequence length, right? Then we have your forward, and I'm just going to return self.embedding and effects, right? Like we're not doing anything fancy here. This is just the token embedding. Next up, I'm actually going to build the transformer block. So first we're going to need the attention, so I'm just going to set it up as a class, and we're going to go into a pretty decent amount of detail with this one, right? So again, init config and forward self comma x, and yeah, so I'm going to go into a little bit more detail into this one. First we got to obviously set some stuff up, and this setup doesn't actually, this isn't, the setup here isn't too fancy. It's the actual forward that's super interesting, so I'm just going to set it up. So obviously we want to know the num heads because that's the number of attention heads, so that's config.num heads. Then obviously we want to set up the head dimension. So this is just how big each head will be. So that'll just be config.embed dimension, and we're going to like float divide that by the number of heads. And so then the scale, right? So this is like how much smaller and bigger we go. That's just going to be the square root of the head dimension, right? Next, I'm going to set the thing that actually takes the input and turns it into a query key and value as, so I'm going to call that self.qkv, query key value, and that's just a linear layer, right? We're effectively just taking the size of a embed. So config dot embed dimension, and then the output features is just going to be the 3 times that, right? Like, right, because we're effectively scaling up by 3 to get a query key and value. Next, obviously, the dropout. And so I'm just neural network dot dropout, and so the size is obviously, well, the dropout rate is obviously the attention drop rate, and so obviously this is 0 in this instance, so you probably don't even need a dropout, but like now you can just change the number from the config, so it's super easy to like try some different stuff, and I recommend you do. Just try a bunch of different stuff, see how that affects the trading and whatnot. Next, obviously, we have the proj, and this is just like a linear layer to like bring it back into like it's basically just so like just the end to like clean up some outputs, right? So network dot linear input features config dot embed dimension, and we're outputting again config dot embed dimension, and obviously dropout, and that's again a dropout layer and config dot drop rate. Right, so now that's the setup. Now we actually do the attention calculations, right? And so what I'm going to first do is I'm just going to split up the x into the batches, the number, and c, and that's just the x dot shape, right? So that's just how big these are, and then we can actually do attention stuff here. So first we're going to follow it through the QKV layer. So this is the queries, keys, and values. So that's self dot QKV of x, and we're obviously going to reshape it, right, so that it's actually in splittable in the format. So obviously we're gonna keep the b and the n. We're gonna split it, 3 ways, and we're gonna change the size so it's, so that each head has its own thing, and c divided by number of heads. And so c is just like the number of tokens we're dealing with, context, right? And so we're splitting it up into 3, and we're effectively also turning it into like a square, right? So now you have the number of heads on one side and all what any given head is dealing with, q, k, and v. And so again, we're also going to just permute over it, right? 0, 3, 1, 4. Right, we're just going to permute over it so that we actually have this up. And then we can actually pull out the query key and value. And so that's just QKV of 0, then QKV of 1, and then QKV of 2, right? We're just pulling out the queries, keys, and values from the QKV. Now, the attention. The attention is effectively, we're doing a dot product, or kind of like a matrix multiplication, but like it's on vectors, so it's a dot product. Query at k. And we're obviously going to transpose k because we have to make sure that they have the right dimensionality. Transpose minus 2 comma minus 1. And then we're going to multiply this by the scale, right? So this is just, scaling it back up. Next, we're going to apply softmax. So we're going to apply softmax, and we're just not going to change the dimension here. And then we're going to do the drop, right? Attention. Self dot attention drop of attention, right? So now we have the attention, and next we're going to dot product it with v, right? Like the value. X equals then the attention, dot producted with the value, and obviously we have to transpose the value. Minus 2 comma minus 1, sorry, 1 comma 2. And then we're gonna have to reshape it. Hold on. No, this is the right one, but you have to transpose it at the end. Transpose, 1 comma 2, and then we have to reshape it to B and C. Right, and then we're just gonna do the output stuff, like x equals self dot proj of x, then x equals self dot proj drop of x, and then we're just gonna return x. Right, and so as you can see here, we're effectively taking all the queries and dot producting them with all like the keys, and then what we're doing from there is we're effectively bringing that back together with the value, and then just reformatting the dimensionality to make sure it like makes sense. And that's effectively the core calculation of a transformer, right? You take any given thing and you do attention. Next, you have your MLP layer, and this is going to be just a lot simpler, right? We're just going to have like a fully standard MLP layer. Again, this imports from neural network.module, and you know, you obviously have your default setup, right? And then forward x, right? And so here we're just going to set up the bunch of layers. So self dot, and it's just a linear layer, so I'm just going to call it linear layer 1, neural network dot. I guess this is, it's not really a linear layer. Yeah, it doesn't particularly matter. I'm just going to call it L1. Config dot, we take in the embed dimension, and we turn it into an integer, right? Because we have it converted to an integer. It's just the embed dimension times the MLP scale, right? So now we're basically just making it bigger, and then, you know, doing Gaussian and bringing it back smaller, right? So int config dot embed dimension star config dot MLP, it's lowercase, MLP ratio, right? So again, in this instance, it'll be 4, and we're basically making it 4 times bigger. And then we'll bring it smaller again. Then self dot act, so the activation function, that's just going to be, I'm just going to use Gaussian, right? Like, it works, no reason to change it here. And then linear 2, neural network dot linear in is the integer. We're again basically just going to bring it back down to the embed dimension. So config dot embed dimension star config dot MLP ratio, and the output features is config dot embed dimension, right? And then from here we're just gonna have dropout, right? Dropout, and I'm just gonna use the dropout rate, the drop rate, right? Next, when actually returning it, we're just gonna go through all of these, right? So x equals self dot ll1 of x equals self dot the activation function of x equals self, and we're going to do dropout drop of x equals self dot linear 2 of x, then we're going to do dropout again, x, and then we're just going to return x, right? We're just going to run through all of these layers, and then we're just going to return the output. Now we can actually make a transformer block, right? Like class, I'm going to call it transformer block, right? And then we're importing neural network dot module, right? And again, the standard stuff. Self, comma, config, def forward, self, comma, x, right? And hold on. Oh, I forgot to do the super. I realized I forgot to do that. And of course, this is necessary for the neural network. And so then, editing the block, again, we have to do that. And then now we can actually do the block. And the block is just very simple, right? We're just doing layer normalization and then attention, right? So block, I use self dot and normalization 1 is neural network dot layer norm, and a normalized shape is again config dot embed dimension. Yank that, and then again the attention neural network dot not neural network. We're using our own attention, and then the config. We're feeding into the config, right? Then we're going to have another normalization in between the two layers, similar to Transformers paper. Watch that video if you haven't already. And then self.mlp equals, we're going to use our own MLP of config. And there we go. And then now we can run through the forward, which again, x equals x plus self.attention, self.n1 of x. Right, we're feeding through the layers. Obviously, we have the residual here, right, from the transformer paper. Plus self.mlp self.n2 of x, right? We're doing the layer norms, and then we're gonna return x, right? We're just running through the layers. Now we can actually make a fully fledged transformer, right? Last transformer, neural network dot module, right? And again, we do our regular thing. Def under init, self config, def forward, self x. We bring down the init, and then what we're just going to do is we're going to set up a bunch of stuff. So self.config equals config. So if we need that, well, if we need that in the next in the forward, we can use it. You can just get rid of it if you want, but you know what? I'll get rid of it. Whatever. Self.token embed. So this is the actual token embedding. So we're just going to pull in the token embedding we made earlier with our config. And our position embedding, right, from the transformer is we're just going to set that as just like a parameter that the model can change, right? And so the parameter, it's just going to start out as a bunch of zeros. Right, it's not the Canadian zeros. And the size, it's 1, config dot max sequence length, and it's also the embed dimension, right? Like dot embed dimension, right? We're just having a bunch of zeros. And obviously this is just going to be trained and whatnot. This is just doing the init. Next, self dot the position dropout is, again, if you can guess, it's a dropout, right? And then it's going to take config dot drop rate, right? Then we're going to get the blocks, right? So we're just going to create all the transformer blocks. And so that's just going to be a neural network dot module list. Right, so we're just making a list of all the modules. And so it's a list that takes in, well, it's transformer blocks of config for underscore, because we don't actually care about this variable, in range config dot depth, right? Then from here, self dot norm equals neural network dot layer norm, right? We're just doing the final ending layer norm, config dot embed dimension, right? And then self dot head equals neural network dot linear, and this is just your output, right? Like config dot embed dimension, and the output features is config dot vocab size. Right, and so if you watch my Vision Transformers video, you can see that vocab size takes the place of the prediction, right? This similar thing, it's just we're effectively predicting what the next token is to come. There you go. You have the vocab size. So now to actually do the forward, x equals self dot token embed of x equals x plus self dot position embed of, obviously we have to actually get the right one, so we'll set as colon, comma, colon, x dot size of 1, comma, colon, right? So we're just getting the specific one we want. And then x we're going to do is the position drop, self dot position drop of x. Now from here we're just going to go through all the blocks. So for block in self dot blocks, x equals block of x, which is running through all the blocks. Then we're going to run through the normalization in the head, so x equals self dot norm of x, and then x equals self dot head of x, right? So this is just, and we're going to return x. And this is just, this is a full transformer, right? This contains everything we need. And so from here, I'm going to go and go through the training code. Okay, so as usual for the training code, because it's not as interesting, I'm just going to go and bring the code over from a previously prepared training file, and I'll just explain it as we go. Right, so open up train.py, and so obviously, first of all, what we're going to do is we're going to have our imports, right? We're importing transformer, we're importing TQDM, which is going to help us with training stuff. We're importing requests so we can get our training data, and we're importing the data loader data set and a bunch of the optimization functions and whatnot. Then what we're going to do is we're going to set up our hyperparameters for our training, right? So our hyperparameters, they're going to be batch size of 255. I'm just going to do one epoch because this is a pretty large data set. Learning rate 3e minus 4. I will use CUDA as usual, and the sequence length is 100, right? The maximum context is 100. And so it's 100 simply because VRAM limitations and compute limitations, because as you know, transformers grow quadratically with the sequence length. So if I were to set this 10 times bigger to 1,000, it would actually be 100 times more compute I have to do, and I just don't have the compute for that, right? Then what I'm going to do is actually download the dataset, right? So you have the Tiny Shakespeare dataset from Andrea Karpathy's GitHub, and we're effectively just getting it and getting the text from it. And so now we actually have to create the vocabulary. So we're going to do our own tokenization, and by creating our own tokenization, I'm just going to do it on characters, right? We're not doing anything fancy, it's just on characters, right? So we're copy. Right, it's literally just on characters, right? We're gonna get all possible characters here, and then we just have a tokenization, right? It's nothing fancy. And then what we're going to do is then we're just going to actually initialize the model, right? So we're going to set the vocab size to the vocab size and the max sequence length to the sequence length, right? So these I'm overriding the actual config because the vocab size is actually depending on the data set, right? So if I take a different percentage of the data set, it will have a different vocab size. And the max sequence length is, again, depending on hyperparameters. So I'm going to be using 100 here, right? And so then I'm actually going to create the dataset class, right? So here you have the dataset, and this actually, will get all the stuff in the Pytorch dataset format. And so from there, what we can do is we can create the train and test sets and the loaders and whatnot, as well as the base model. So again, this is pretty self-explanatory. You have the dataset, it's the Tiny Shakespeare dataset. We're splitting up into train and test datasets, and then we're doing a random split, and then we're creating data loaders for them, right? And then we're actually taking the model and putting it to our device. Next, obviously, we had to set up the optimizer and the loss function. So we're using cross entropy and NMW like usual. We're using cosine annealing, right? This is just fully default stuff, like NPC criteria and optimizers and whatnot. We're not reinventing the wheel here, right? Then obviously we need to train and test functions, right? So train, we're going to do train, and then for the batch, right? We're just going to, do train and test functions, and then what we're going to do is we're just going to have a train loop, right? So we're just going to have a training loop, right? And so our best loss is obviously going to be infinity because we're trying to go to 0. And then, we're just going to iterate through, and then as we go through the data, loss is going to come down. And this is effectively all the code we need. Now, of course, what we also want to do is whenever we, say, run a few batches, right? So, doesn't really matter. We'll do it at the end. Just whenever the training data is done, what we're going to do is we're just going to sample some outputs of it, right? Hey, we're starting with Romeo. What will Romeo say, right? And then we'll take that as an input sequence, put it on a device, and we're just going to generate a string, right? So we're just going to get the model, and we're just going to iterate through it until eventually we have a generated text, and we're going to output that. And that's all the stuff. I will get back to you when the training is done, and I'm going to change some hyperparameters so that the training is a lot shorter, right? I'm going to run on 10% of the training, right? We're not going to do the entire training run. This is going to be a small 6-minute run. Normally it's going to take an hour, but you'll kind of see some smaller semblance of results in 6 minutes, and then you can run the whole training run. It's only going to take an hour with one epoch. If you want to do more. And so, I'm going to run the training run now. And, I'm having issues. Failed to initialize NumPy. I realized I forgot to install NumPy. Right. And then there we go. Now we're going to run a training run. This is only going to take 6-7 minutes. It's going to be a very short training run. And then, as always, you can expand this later and whatnot. I will get back to you when the training run is complete. Okay, so the training is now done and it only ran through 10% of the data set. So as you can see, it's not super good outputs. However, you can kind of see some of the Shakespeare structure in the text with what Romeo's saying. He's saying dear, and then this character Manan, and he's just going on like a soliloquy. And so, obviously, if you train over the entire data set, you get better results. And if you did the whole thing, you get better results. And so, in summary, that's basically it on training a transformer. You can train it for longer to get better results. You can make changes to get better results, right? This is just a quick demo to see, hey, we can train a transformer. And so, obviously, before this, you get pure gibberish. After this, you get nice text. And so from here, I'll leave it to you guys. I hope you enjoyed this video. Please like and subscribe, and I hope you all have an amazing day. Thank you for watching.